Hello everyone, this is Mr. Milne. I'm here with an instructional video on finding segment lengths in circles. So before we start, I'm going to just remind you briefly about the three different types of segments we're going to be talking about today. And the first is a chord, and a chord is a segment that is formed by connecting 2 points on a circle together. This segment is completely contained in the circle. So it doesn't go outside of it, it just stays inside of it. It goes from one end of the circle to the other. That also means that a diameter is a chord, but we typically refer to something like this here at the bottom, where it's from one end of the, or 1 point on the circle to the other, and it stays completely inside. So this would be a chord. The next is a secant, a segment or line that passes through a circle in one or both directions at 2 points on the circle. So typically you'll see one that goes through at least 1 point in the circle, and then it'll stop at the second one or something. So for instance, like that, that would be a secant just as much as this would be a secant here. Unlike the chord, the secant goes through a circle. It doesn't just stop inside of it. Okay, so this would be a secant. And then the last one would be the tangent. And a tangent is a segment or line that touches a circle at a single point, which is called the point of tangency. These segments or lines will never pass through the circle. And so an example of that would be up here on the top left. The tangent line only touches the circle, it never goes through it. Okay. So if we're looking to determine segment lengths from chords, secants, and tangents in circles, there are 4 different cases. Okay. The first one is the case of 2 tangent lines. And what this says is that if 2 tangent segments to a circle are drawn from the same point outside the circle, then the lengths of the tangent segments are equal. Then that means that the tangent segments are congruent. So let's say, for instance, that you have point A here, which is a point outside of the circle. Everybody can agree with that. And you've drawn these 2 tangents here. So you've drawn tangent A to B because it's tangent at B. Okay, that's a point of tangency. And you've also drawn from A to C, which is another point of tangency. Okay. So what this theorem is saying is that since they both originate from the same point outside the circle, they originate both from A, that AB and AC would be congruent. So of course, when we mark congruent segments, we mark them using little tick marks here. So AC and AB would be congruent. All right. So do you see any other tangent segments that would be congruent here? Well, you should see that FB and FE would be congruent. So FB would be congruent to FE. And you should also see that CD and ED would be congruent as well. Okay. So for instance, if we say that AB is equal to 10, FE is equal to 14, and DC equals 4, I'm going to go ahead and label all of those. 14 and 4. What are the lengths of AF, DF, and AD? So first off, if we know that all of these are congruent, then we know that AB and AC are the same. So AC is 10, DC and DE are the same. So DE is 4. And EF and BF are the same. So that is 14. So AF is consisting of AB and BF. So 10 plus 14, which is 24. DF consists of DE and EF. Adding them together, we get 18. And AD, 10 and 4 gives us 14. So with tangents, two tangent lines like this, those are congruent if they originate from the same point outside the circle. All right. So let's look at case 2, and case 2 are two secant lines. And the product of the length of one secant segment and its external part, so the whole secant segment times its external part, so this is for secant 1, okay, and then for secant 2, this product is equal to the product of the length of the other secant segment and its external part. So it's the same thing on both sides, just with two different secants. So this is the first secant, this is the second secant. So if we look here at our diagram, we have two different secants here. The first one is AE, so that would be our whole. AE would be our whole thing. So this is AE times the external part of AE. Now what that external part means is that it's outside of the circle but still part of the secant. So the external part would be AD because it's outside of the circle. And that's going to be equal to the whole other secant. So the other secant is AC times the external part of the second secant, which is AB. Okay, so in this case, you've got the whole thing times the external equals the whole thing times the external. So let's look at an example here. It says if AC is equal to 12, AB is equal to 4, and AE equals 16, determine the lengths of AD and ED. So here we have a whole part labeled, both of our whole parts labeled, and only one external part, and AD is our other external part we're looking to find. So if we're looking to do that, we're going to take the whole segment first, so 16 times its external part, which is X, and that's going to be equal to the other whole thing, which is 12, times its external part, which is 4. So 16x drops down, 12 times 4 is 48, divide both sides by 16, and we get that x is equal to 3. So AD is equal to 3. And so since we know that AD is 3, then we know, and we know the whole thing is 16, we can take 16 minus 3 and get 13 for line segment ED. Okay. All right, so let's flip on over to the next case, and the next case is going to be one secant line and one tangent line. So with one secant line and one tangent line, the theorem states the product of the length of the secant segment is an external part, so it starts out the exact same way as the two secants, equals the square of the length of the intersected tangent segment. And so in words, or in little parts here, the whole secant segment times the external part is equal to the tangent part squared. Okay. So your whole secant, which in this case would be AD, times your external part of the secant, which would be AC, is equal to the tangent, which is AB squared. And the reason that this works is it's very similar to two secants, because really what you're doing is a whole times external twice. And what I mean by that is the whole tangent here is equal to AB. But since the tangent never goes inside the circle, the entire thing is considered to be the external part. So the whole times external gives you AB times AB, which is tangent squared. So with one secant line, one tangent line, you're still doing whole times external, and you're just squaring your tangents. So here it says if AD equals 9, and AC equals 4, determine the lengths of AB and CD. Well, CD is fairly simple because it's already mostly done for us. So our whole thing is 9, our external part's 4, so the internal part would be 5. So CD is equal to 5. All right. And then to determine the length of our tangent, which would be AB, we need to use our formula. So whole times external, our whole thing of the secant is 9 times the external part, which is 4, is equal to the tangent squared. We don't know what our tangent is, so we just have x squared. 9 times 4 is 36. We're squaring the x, so to get rid of that square, we need to square root it, and we get 6 is equal to x, which is what AB is. And then our last case here is case 4. This is for two chords, and the theorem states if two chords intersect in a circle, the product of the segments of the chord equal the product of the segments of the other. In other words, what this is saying is that for chord 1 and chord 2, we can say that the product of the two parts of chord 1 is equal to the products of the parts of chord 2. So if we look at our diagram here, we're going to see that we have a chord CD, and the two parts of it are CE and ED. And then our other chord has parts AE and EB. So for example, if AE equals 4, CE equals 5, and DE equals 8, determine the lengths of EB, AB, and DC. Well, DC, we already know what the two parts of the chord are, and that would be 8 and 5, so DC is equal to 13. In order to determine AB, we first need to find EB, so we need to use our theorem, which states that part times part equals part times part. So the two parts of the chord for AB, 4 times x, is going to be equal to 5 times 8. 4x is equal to 40. Divide both sides by 4, and we get that x is equal to 10. So the length of EB is 10. And that means that the length of AB would be 4 plus 10, which is 14. Now there are a couple other theorems that do show up. So this is the radius tangent theorem. It states that if a tangent line and the radius of a circle intersect at the point of tangency, then the tangent line and radius are perpendicular. And so what that means is that the radius and this tangent will form a right triangle with one another, which means that to find this missing side here, if you want to find it, you have to use the Pythagorean theorem. Okay. And remember, your Pythagorean theorem is a squared plus b squared equals c squared, where a and b are your legs and c is the hypotenuse. So in this case, you would have 6 squared plus 8 squared equals x squared. And if you work that out, you would find that x is equal to 10. So in some cases, you will have something that looks like this. On the other hand, you do have something called the radius chord theorem. If a radius of a circle is perpendicular to a chord of the circle, then the radius bisects the chord. So what it does is it splits it into two. Okay, so same deal though. The radius from one end of the chord to the center would form a right triangle if it bisects the chord. Okay, so if the radius is perpendicular and it bisects the chord, this is a right triangle as well. So you would be using the Pythagorean theorem just like that. And in this case, to find x, you would have 4 squared plus x squared equals 5 squared. Okay, so let's look at some examples of these various theorems here. And the first thing you're going to want to check before you start is what type of segments, lines, or whatever else do I have in the problem, and then determine which is the correct formula for you to use. So in number 1, it says, what is the value of x? Now, it says DE is tangent to the circle at D, and EG intersects the circle at points F and G. So if you look here, we see that we have a tangent, ED, and we have a secant, EG. So we have one secant, one tangent, and so if we have that, then we are going to use the case with that, which is whole times external part equals tangent squared. So the whole of the secant, what is it equal to? Well, the two parts of the secant are 2 and 6. So that means the whole thing is equal to 8. So 8, and then times its external part, which would be 2, is equal to the tangent squared. Well, tangent is x squared. 8 times 2 is 16. Square root both sides to get rid of the squared, and you get that x is equal to 4. All right, number 2, points are, R, S, and T are points of tangency. If Rx equals 8 and Ty equals 7, what is the measure of xy? So here, all of these points are points of tangency. So all of these points are, or all of these segments are tangents. Okay, so all of these segments are tangents. So we have the case of 2 tangents. So if we know that Rx is 8, what else do we know would be 8? Well, the tangent that originates from the same point, which would be x, would also be equal to 8. So that would be xs. Those two are congruent. And then here, if ty is 7, what else is 7? Well, that would be sy, because they both originate from y. So now we know what ys is and what sx is. So xy is simply 8 plus 7, which is 15. All right, number 3. It says chords FG and KM intersect in the circle, forming the segments with the measures shown. What is the value of X? So we have two chords here. So when we use that formula, we have part times part equals part times part. So our first chord's parts are X and 4. So we have 4X. And our other two parts are 5 and 12. So 4X equals 5 times 12. 4X drops down. 5 times 12 is 60. Divide both sides by 4. And we find that X is equal to 15. Number 4, secants HL and HM intersect the circle below at points X and Y respectively. What is the length of HX? So we have two secants here, which means that we're going to be using the formula whole times external equals whole times external of the other segment. So it doesn't matter which one you pick first. I'm going to start with the one that has X in it. So the whole secant there is equal to 20 times your external part, which is X, and then is equal to the other whole secant segment, which in this case would be 18 because you have to add those together, times the external part of that one, which is 10. 20x drops down. 18 times 10 is 180. Divide both sides by 20. And you get that the length of HX is equal to 9. Number 5, in circle A, BC equals 24 centimeters and AD equals 9 centimeters. What is the length of AC? So if we look at this problem real quick, we're going to notice that we have a right triangle here. So the radius, if we were to extend this out completely, the radius is perpendicular to the chord. And what that means is that the radius is bisecting the chord. It's cutting it in half. So if that cuts it in half and the whole chord is 24, then both of these parts are going to be equal to 12 centimeters. Okay. So now to determine AC, we have to use our Pythagorean theorem. So A squared plus B squared is equal to C squared. A and B are our legs, which in this case are 9 and 12. So 9 squared plus 12 squared equals the hypotenuse squared, which is AC, which is what we're trying to find. 9 squared is 81. 12 squared is 144. 81 plus 144 is 225, which is equal to x squared. Square root both sides, and you get that 15 is equal to x. In some cases, what it will do as well is it'll ask you to find something, but then it'll want you to find this portion of it, like from this point to the end of the circle. Well, A to the end of the circle is the radius, which would be 15. So 15 minus 9 would give you 6 here. So just in case that it wants you to do that, I just wanted to mention that. And then number 6, it says chords LT and SM intersect at point E, as shown in the circle below. What is the length of SM? So this is a situation with two chords. So we take the part times part equals part times part. So our first segment here I'm going to use is the LT one, which is 6 times x. So 6x. And then I'm going to take 2x minus 5 times 8. Don't forget to distribute your 8 out. So you get 6x equals 16x minus 40. I'm going to subtract 16x from both sides, and you get negative 10x equals negative 40. Divide both sides by negative 10, and you get x equals 4. It doesn't want x though, it wants the length of SM. So we have to plug in x here, but SM is this entire thing. So SM is going to be equal to 2 times 4 minus 5, and then plus the 8. 2 times 4 is 8. 8 minus 5 is 3, plus another 8 is 11. And that's going to do it for this video, guys. I will say that you're going to have a test soon on this stuff. So make sure you work on the worksheet. Also make sure you watch the other video on arc lengths and sector areas, just so you know how to do those, so you can do both of the assignments that have been posted. Thanks, guys, and I will see you in the next video.